This is Lecture 5. It's going to deal with alchemy and its relation to chemistry. Most of us have at best a vague acquaintance with alchemy. It conjures up all kinds of images. The first things folks usually think of when alchemy is mentioned are the search for the philosopher's stone, or how to change lead into gold, and the quest for a medicine that imparts immortality. The only allusion to alchemy I've made so far in this series was to note that Newton was vitally interested in it. We're going to become more familiar with alchemy today, especially as the practice of alchemy began to be criticized in the 18th century. Of course, today we immediately want to distinguish alchemy from chemistry. Chemistry we know about, at least today's chemistry. When I mentioned chemistry last time in our exploration of mineralogy and the analysis of rocks, I didn't stop to tell you much about what I meant by the term. There I simply said that the German mineralogists were interested in what chemists knew about the interactions of earths with acids and bases. Both chemistry and alchemy were pursued in the 18th century, but as we'll learn next lecture, the second half of the 18th century saw major advances in chemistry. By the end of the 18th century, chemistry had taken on a new status from what it had earlier. In this lecture, I want to examine how this new status emerged from the older links chemistry had to alchemy. We'll see how, in spite of alchemy's continued presence in the 18th century, the new Enlightenment emphasis on reason had an impact on it. What happened was this. As the Enlightenment value of rationality became more and more visible and desirable, it provided a means by which some attempted to differentiate themselves from alchemists. This began happening in the early years of the 18th century. I have to tell you, it wasn't as simple and straightforward a matter as it might sound. Looking back on this development, it's hard for me to see the ones who began complaining about alchemy the loudest in the early decades of the century as all that more rational than the others, the ones that weren't. The one German physician and natural philosopher who we'll talk about wanted to call rational chemistry a different enterprise from the alchemy that he saw all around him. Now, he thought he was being rational, and I know what's important here is that he thought he was being rational and the alchemists were not. I agree, that's important. But if from our vantage point we can't see what being rational meant as clearly as he did, that suggests that maybe there were other reasons as well why he railed against alchemy. It wasn't just that it was so irrational, even if he thought it was. There were other associations it also possessed. They were undesirable, social, for example, or religious associations that made him want to dissociate himself from alchemy. It's as if he were saying, look, I'm not one of those guys, but I'm getting ahead of myself. Let's learn a little bit about alchemy and chemistry. The general context of our considerations in this lecture has to do with understanding how material substances combine. In the 17th century, there were different approaches to this subject. I should let you know right away that here in the 17th century, we have both the terms chemistry and alchemy, but they're not cleanly distinguishable in this period. Chemistry, spelled incidentally C-H-Y-M-I-S-T-R-Y in English, is in fact the more inclusive term. Chemistry involved the study of elements and the essential principles that combine to form bodies. What did this mean? Well, there were several schemes of elements and principles according to which all bodies were thought to be composed. I'm sure you're aware of the four ancient elements: earth, air, fire, and water. To these were added various material principles. A common scheme included three principles: mercury, sulfur, and salt. Any substance that was volatile and vaporizable clearly possessed the principle of mercury. Things that burned and were combustible were imbued with the sulfuric principle, and the quality of being fragile or separable meant that the principle of salt was present. So it wasn't merely a matter of elemental substances. There were principles present, and that played a part as well. Chemists were the ones who knew what the elements were and what principles were present, so they could use this knowledge to bring about chemical change. For example, chemists wanted to learn if it was possible to extract principles and elements from bodies, then later add them back to reconstitute the bodies. Now why? Why would they want to learn how to do this? Well, first, there's just the idea of learning something new, knowledge for knowledge's sake. But more fundamentally, the new knowledge also adds to our philosophical understanding as well. Especially as what's been called the new science of the 17th century gained more and more visibility, chemists had a larger agenda to be part of. For many, it functioned to bring greater glory to God, the same motive we've already met so often in other areas of natural philosophy. But there was more to it than this as well. They wanted to know how to take substances apart and put them back together for practical reasons too. This kind of knowledge could be helpful in purifying substances of impurities, for example. Or it might help you learn how to transmute one material into another. And depending on what you started with and what you ended with, that could be very useful. And who knows? Experimenting with chemical change might lead to new, stronger medicines or metals. But there was an implication of this practical side of chemistry that I have to call your attention to. You see, just like in our own world, in early modern society, there was a social hierarchy associated with various vocations. Those who engaged in the practical arts didn't stand as high up on the social scale as those whose pursuits were purely intellectual. Pursuing philosophy was one thing, but vocations where you got your hands dirty, that was another matter. Now, I'm going to say more about this, but for now, let's just realize that chemistry was kind of caught in a bind, since it had an interest both in philosophy and in the practical arts. In the 17th century, as long as it kept its association with the practical arts, it was going to be hard to enjoy the status of pure natural philosophy. So much for chemistry. Let's turn our attention now to alchemy. Then as now, alchemy was seen as an endeavor primarily interested in the process of transmutation. That's one reason why I identified chemistry as the more inclusive term. Chemists, too, experimented with transmutation. But they were just as engaged with other things as well. Alchemists, by contrast, were known for their interest in changing one material substance into another. Now, the classical alchemical pursuit of transmutation was very much alive in the 17th century. This is evident, for example, in the great number of works published on the subject. Not only so, but numerous outstanding figures from the period were among those who wrote them. That included natural philosophers like Robert Boyle and Isaac Newton, both of whom investigated the possibility of alchemical transmutation. So we need to notice something here. If men like Newton, natural philosopher par excellence, if his like was engaged in alchemy, then clearly he didn't see it to be contrary to his work as a natural philosopher. What I'm saying is that increasingly, alchemical experimentation was pursued with a view to advancing natural philosophy. Now, I find this interesting because it means that alchemists were caught in the same bind as chemists. As long as they remained associated with the practical arts, they would have lower social status. In fact, of the two, chemistry and alchemy, it would seem harder for alchemists to overcome the stigma of the practical arts, since that was what they'd always been known for. I do find it interesting, however, that some natural philosophers of the 17th century, and some noted ones at that, believed that alchemy, in fact, had an intellectual side. It contributed to natural philosophy. Now, there were signs prior to the beginning of the 18th century that chemistry was beginning to differentiate itself from alchemy. For one thing, chemistry had begun to see itself as a separate investigative enterprise. One way this showed itself was in the chemistry of salts. Experimentation in the chemistry of salts led in some quarters to a replacement of older conceptions of composition. Remember that in the older scheme, substances were made up of elements and principles. Some chemists were now working with new schemes where salts were concerned. They were using what they felt were more practical notions of acids and alkalis. Another measure of the separation of chemistry from alchemy could be seen institutionally. When the French Academy of Sciences was founded in 1666, it incorporated chemistry as a major activity from the start. Now, if anything could make chemists visible or associate them with the new natural philosophy, inclusion in this new institution of natural philosophy would surely do it. This is not to say, of course, that none of the chemists in the Academy was interested in transmutation. That I doubt very much. As I mentioned earlier, chemists were interested in the process of transmutation. They just felt that it was only one kind of material transformation. It simply means that chemists were coming more and more to the fore as chemists. The lines between them and the alchemists that had earlier been more blurred were becoming more distinct. After the turn of the century, the chemistry of salts, which resulted from the interaction of acids and bases, had developed to a point where we begin to see attempts to summarize what combines with what. A prominent professor of chemistry in France did this in 1718 at the Garden of the King, that scientific institution I first mentioned in Lecture 1. The chemist's name was Etienne Geoffroy. Here's what he wrote. Every time two substances which have some disposition to join together, one with the other, are found together, if a third one arrives which has more affinity with one of the other two, it unites with it, causing the other to be let go. Now, I realize that doesn't sound terribly profound to your ear, especially if there's a basic chemistry course somewhere in your past. But what Geoffroy was saying was that there are degrees of affinity. This is implicit in what he said because some affinities, being stronger, displace others that are weaker. If so, then we might be able to arrange the substances in a table according to the strength of their affinity. In fact, he published tables of what were said to be the affinities observed between different chemical substances. All right, let's review what we have so far. For much of the early modern period, the line between chemistry, which was concerned with all kinds of ways that material substances interacted, and alchemy, which was primarily interested in transmutation of one substance into another, the line between chemistry and alchemy was blurred. Both involved experimentation, and that associated them with the practical arts. Both also contributed to natural philosophy, increasingly so as the 17th century progressed. Already before the beginning of the 18th century, however, there were indications that chemistry was being distinguished from alchemy. One indication of this was institutional. Chemistry held a place in the French Academy from its very start. Another indication was the growth in the chemistry of salts, especially after the turn of the 18th century, which distinguished chemistry as a separate investigative enterprise. But because chemistry and alchemy, for that matter, retained an association with the practical arts, the social position of chemists was not as high as it would have been if it had been a purely intellectual field. What we see occur in the 18th century is something new. Some chemists, saddled with a status they believe was unworthy of their field, decided to try and upgrade it. Now, they didn't get together and say, look, we've got to do something about our status. I'm not saying that the tactic I'm about to describe was even a conscious ploy they used to improve their status. But clearly, their attitude was to bring new respect to the practical side of their work. The problem was that the folks in society who were associated with what's been called the craft traditions were often regarded as artisans, people who worked with their hands to produce a product, and they stood lower in the social scale. These were the people concerned to make a livelihood. They weren't valued in society like others. And that association that chemists and alchemists had with the practical arts made many see them as artisans. Let me be a little more specific about the social divisions here. Above artisans stood the educated ranks of society. Some of the educated enjoyed very high social status. For example, the clergy had exemptions from paying the kind of taxes people who worked had to pay. In this, they were like the nobles. They enjoyed a privileged role in society. Clergy, especially the higher clergy, were often very educated people. That stood to reason since they supplied the theologians. So we shouldn't be surprised that many natural philosophers from this time were members of the clergy. But many natural philosophers were members of what was known in France as the Third Estate. That was a designation given to everyone who was neither clergy nor noble. The Third Estate was known as those who work. The other two estates, the clergy and the nobility, were those who pray, and since the military officers often came from the nobility, those who fight. The vast majority of folks then were in the Third Estate. Now, within the Third Estate, education made a difference in your social status. It couldn't by itself raise you out of the Third Estate, but it could bring you more respect within it. Clearly, lawyers, physicians, and professors commanded a higher social status than artisans did. Back to our chemists and alchemists. Saddled with an association with the artisans of the craft traditions, chemists in particular wanted to improve their status. What we begin seeing in the 18th century is an attempt to bring their education to bear on the craft aspect of chemistry. Some chemists began to expand the craft traditions with which they'd been associated to include a rational intellectual focus. They began arguing, that is, that chemical experimentation was not at all the work of mere artisans, but an intellectual enterprise that required a special understanding. Well, nothing I've said so far would not also apply to alchemy. I said, didn't I, that men like Newton had begun incorporating alchemy into their natural philosophy? Wasn't that the same thing as what the chemists were doing when they demanded that chemical experimentation was an intellectual matter? Yes, it is. But the chemists were making a claim that the alchemists could not. They were saying that the particular kind of intellectual activity that one must master in order to do chemical experimentation was rational activity. As we know, rationality was the emerging value of the time. I virtually identified the Enlightenment with it. So chemists were on the cutting edge with this claim. They were going with the future. Alchemy might have been philosophical in the eyes of Newton and Boyle, but although Newton regarded it as natural philosophy, not unlike astronomy, most people didn't see it as Newton did. Most did not think of it as being distinguished by its rational qualities. This then gave chemists a means by which they could try to upgrade their status. They could argue, look, chemistry is an intellectual matter even when it conducts experiments. It did mean that they'd have to distinguish themselves from alchemists, but so be it. I want to give you an example of what I mean here by telling you about the work of an important figure from the history of chemistry from the early 18th century. I'm talking about a physician named Georg Stahl, who was professor of medicine at Halle and later court physician in Prussia. Stahl is important because he tried to create what he called rational chemistry, and in doing so, he set it in direct opposition to alchemy, which he did not believe was rational. Stahl insisted that the meaning of the words alchemy and chemistry, which he acknowledged had been used for a long time interchangeably, had recently come to denote two completely different undertakings. Now, in what follows, I want you to listen to see if it's clear to you exactly what Stahl means by rational, whatever it is that made it so different from alchemy. You'll hear a lot of reasons why chemistry is different from alchemy, but I want you to watch and see if it's as clear to you as it was to Stahl what being rational means. Stahl begins by identifying alchemy as the mostly confused and largely vain attempt to make gold. Chemistry, he said, was different because it was devoted to rational experimentation as a means of expanding fundamental knowledge of natural substances. Now, Stahl did not think transmutation was impossible, Chemists were interested in transmutation as one of the kinds of chemical change, but things had gotten blown all out of proportion by the alchemists, Stahl thought. That's all they were interested in, and their motives were suspect. Both Stahl and his followers criticized alchemy severely for its negative impact on society. How? For one, it encouraged swindling and promoted a longing for gold and fantastic medicines. One can hear the subtext here. Honest and upright chemists aren't the kind of people who engage in swindling. That's beneath the dignity of a natural philosopher. As if to make the subtext clear, Stahl, who was a very religious man, added that in enticing folks with the prospect of quick riches, alchemy distracted its enthusiasts from their obligations to God. Clearly, the base motives many followed when they practiced alchemy were incompatible in his mind with the moral virtues that God expects of us. Finally, as if to give a practical reason why alchemy wasn't worth pursuing, Stahl threw in that there were no teachers capable of giving rational instruction in alchemy. Stahl then goes on to say what he called true chemistry was. Notice as he does so that he doesn't abandon the association with the craft tradition. His goal is to impart to the practical side of chemistry the emerging value of rationality, to claim for it an intellectual and natural philosophical status. What was true chemistry? Well, first, Stahl said, it was inspired by rational enthusiasm for research. It came from a desire to know the true knowledge of material composition for its own sake, not for material wealth. And finally, he said, it resulted from rational chemical process. Those who knew this rational chemical process could use it to understand how to improve medicine or mineral processing or distilling, brewing, glassmaking, other useful things. Stahl was not, in other words, dissociating himself from the practical aspects of the world of the mineralogist or the brewer or the glassmaker. He was claiming that the chemist's relation to these folks was part of a greater rationality. Now, I can't find in all this exactly what Stahl means by rational. He keeps saying that chemistry is rational, and he makes clear that he doesn't have much use for alchemy, but he never, where I can see, spells out in words why alchemy is irrational and chemistry is rational. We said before that it was important, even when we couldn't understand a historical figure, that we at least have to give him the benefit of the doubt. Stahl felt that chemistry was rational and alchemy was not. That's where he was casting his lot. But fortunately, Stahl does give us a way to see a little more of what he understood by rational chemistry. It's when he actually explains chemical process. There we begin to see what he meant. He tried to construct a chemical system that revealed the intimate composition of substances. The best-known feature of this system was Stahl's treatment of combustion, so let's take a look at it. In putting together his ideas on combustion, Stahl drew on the work of Joachim Becher, a predecessor from the 17th century. Becher had created a system of elements and principles that drew on two giants from the past, Paracelsus and Aristotle. What Becher did was to keep only two of Aristotle's four elements, water and earth, and of them he left only water intact. He expanded the Aristotelian element of earth into three different kinds of earth. These he seems to have based on the three Paracelsian principles of mercury, sulfur, and salt. So he ended up with four component parts of material substances, water, and three kinds of earth. It was one of these earths, terra pinguis, or oily earth, that Becher regarded as the constituent present in all bodies that could be burned. Now, it was in 1702 that Stahl introduced his interpretation of combustion, which was based on that of Becher. He modified it a bit. For example, he adopted the name phlogiston for Becher's combustive principle. It was derived from the Greek word meaning burnt or flammable. He wasn't original with this word. It had been used by others for almost a century when Stahl picked it up. But he's the one who made it famous. Let's explore this phlogiston a little. Phlogiston for Stahl was an imponderable substance. What does that mean exactly? Well, it was substantial, a substance, but it didn't weigh anything. He also believed that by itself, it couldn't be detected by the senses. Now, phlogiston is found loosely present in some substances. That's what combustion was. Combustion occurred when bodies lose their phlogiston. So phlogiston is a weightless substance loosely present in combustible materials whose release constitutes combustion. Take substances that burn easily, say charcoal and oils. They are obviously especially rich in phlogiston. Bodies that can't be ignited or burned, on the other hand, have either lost their phlogiston already or they don't contain any, never had any. Now, Stahl was careful to say that phlogiston was not the same as fire. Fire, after all, can be detected by the senses. Phlogiston was the motive power of fire particles. Using this understanding, Stahl constructed a theory of combustion. Followers of Stahl in Germany then elaborated on his system. The main context in which Stahl illustrated his theory was in the rusting of metals, which he regarded as a form of combustion. He explained the rusting of metals called calcination as their loss of phlogiston. Rusted metals, or calxes, contained no more phlogiston and could not be further burned. So calcination is the rusting of metals to form a calx. Now, you might well wonder about this. If metals lose their phlogiston when they rust, how come they gain weight? If you've lost something, even if it doesn't weigh anything, how come you gain weight? Well, the simple answer is that Stahl was not concerned with weights. He might be giving what he thought was a rational explanation of combustion, but it didn't include weighing, not for him anyway. That, of course, didn't mean that others didn't notice. An early convert to Stahl's phlogiston theory, a man named Johann Juncker, published a history of chemistry in 1730. In it, he praised both Stahl and Becker, but he misinterpreted Stahl on a crucial point. Juncker thought that Stahl's phlogiston was something material. Now, I said before it was substantial, by which I meant that it was something. But as we know, for Stahl, it was not a material thing. Juncker thought it was material, and because of that, he couldn't overlook the gain in weight during the rusting of metals. To get around the problem, he suggested that phlogiston must possess negative weight. In other words, phlogiston buoyed up the metals that contained it, so that when the metal lost its phlogiston to become the rusted calx, the buoyant effect was lost and the heavier weight emerged. That may sound like cheating to you, but aside from that particular adjustment to the theory, Stahl's overall system did provide a pretty interesting account. And it could also be used to give a coherent account of forms of combustion different from merely calcination. Take an ordinary candle, for instance. The theory predicts that if you were to put a burning candle under a glass jar, it should go out after a while because the enclosed space becomes saturated with phlogiston. Once that occurs, no more can be given off. The burning process stops. Of course, that's exactly what happens. Or take the digestion of food, which can be considered a form of combustion. If digestion of food involves burning, then when we exhale, we expel phlogiston-rich air. They did experiments to confirm this. Put a mouse under a bell jar, like we did the burning candle. Same thing should happen. That is, the air should eventually become saturated with phlogiston as the mouse keeps exhaling. Sure enough, the mouse in the experiment dies. So the theory, like good theory anywhere, was linking together rather consistently phenomena from different and related areas. In this case, it was 3 different forms of combustion. Over the course of the 18th century, the phlogiston theory continued to gain adherents in Germany, France, Sweden, Britain. This was because many were finding it very useful in their continued exploration of chemistry. Of course, prior to the middle of the 18th century, Stahl's approach was most well known in the German states. That's where it had originated and been developed by others. But the theory didn't remain confined to the German territories. One reason why not was that there were ever-increasing demands from the growing interests in industry, especially concerning metallurgy, that aroused greater interest in German chemical texts. And as we saw in Lecture 4, if you wanted to know about mineralogy and metallurgy, you'd do well to become familiar with the rich German tradition in that area. So it's not surprising that many German chemical texts were translated between 1750 and 1760, and by 1770, there was a new saga in the history of chemistry about to unfold, and by that time, phlogiston theory enjoyed wide popularity in France and Britain, and had already for 20 years. What new saga in the history of chemistry? Well, that will be the subject of our next lecture.